So today we have the last topic in time series econometrics, and we are going to talk a little bit about non-stationarity. So far we spoke about stationary models, about linear models. We spoke about the conditions of model of series being stationary, like for example, moving average model is always stationary. Autoregressive model is stationary when some conditions hold, and so this is important property because usually we are working with time series in order to build some forecasts, and you build a forecast for the future using the past observations. And so the only condition when we are able to do this is when the future is the same as the past. Then we can take something from the past and somehow extrapolate this into the future. And so formally, and vice versa. So if the future differs from the past, then historical relationships are of no use. So you simply cannot claim that I can take something from the past and use this for the historical forecasts. So the formal definition of this idea is called the stationarity. So stationarity means that the variable that you are observing over time has the same moments, expected value, variance at every point of time. So also the covariance structure is the same, and so on. There was a strict stationarity condition, so here is just a repetition. When you have time series and you take the joint distribution of some, let's say on some interval of these variables, then it doesn't depend. So the joint distribution of these variables does not depend on the time shift. So when you start looking at your observations, otherwise, our variable or our series is called non-stationary, and well, we need to understand what to do in the case of non-stationary time series, because in practice there are a lot of cases when series are not stationary. So first of all, what is the problem? Why we are so concerned with non-stationarity? Because when you try using try to apply the linear models like AR, MA, or ARMA models for non-stationary time series, everything fails. So hypothesis tests fail, conditional intervals fail, forecasts fail, everything fail. So you are not able to make any predictions. These predictions are not going to be reliable, and so simply this is a big trouble for us. First of all, we need to understand that there are two types of non-stationarity, kind of like the two distinct types. So the first one is trend, when series are trending, and the second one is break or breaks, when there are some structural changes in series caused by, well, maybe by some underlying mechanisms that produce this series. So in this lecture, in the first lecture, we will talk about trends, and in the next lecture we will talk about breaks and how to deal with the breaks. So regarding the trends, well, I suppose that everyone somehow intuitively understands what is a trend. So a trend is a persistent long-term movement of a variable over time. So what is important here, that this is persistent, so it persists it exists over a longer period of time. And the second condition, this must be long term, so it's not like 1 hour, for example, and you already you are happy that you identified some kind of trend. And usually time series variable fluctuates around the trend, so it can be under the trend, above the trend, but on average it follows the trend that we are trying to identify. For example, so let me show you here. So this is the series of Russian real GDP per capita starting from 1998 to 2022. And you see that it clearly increases. So it does not show any kind of stationarity. So for example, if you take this period of time, so there is, I don't know, average of something like 40,000 rubles. If you take this period, this is going to be 60,000 rubles. So clearly expected value is different. So it is not stationary, because if you divide the periods into several parts, so the mean and variance would be different. Also here you can see inflation rate in the United States from 1960 to 2022, and again we can see that there is kind of upward trend here from 1960 to 1980. Then there is a decline, so kind of downward trend till 2020, and then again so kind of till 2000s, and then it's almost constant. Then we don't know what's gonna be here, so probably this is just one spike, or maybe there is something else, so we need to keep observing what's going on with this series in the future. So these are kind of visual representations of non-stationarity. So the simplest way how to identify if there is a trend or not is just to plot the series and visually observe what's going on. If you see some development, kind of increase, long-term increase, long-term decrease, then you can be sure that there is a trend. If you see some periods of increase, some periods of decrease, there is also trend, but probably kind of you need to model this trend separately for one part of kind of for one period of time, then for the other period of time. So this is going to be something similar to breaks. Next, we can distinguish two types of trends. So one type is the deterministic trend. So this is a non-random function of time. What is important, this is non-random, right? That's why we call this deterministic. So for example, we can build a model for a linear deterministic trend like this. So t is the time period, 1, 2, 3, 4, 5, and so on. And then it looks like usual OLS with one regressor. So you regress your series at the period t on the order of the time period t here. So this is just a straight line. Another type of trend, deterministic trend, might be quadratic trend. So you just add the second power of your time variable t here. And then you will have something like, not a straight line, but parabola. So it might be like exponentially increasing thing, or probably kind of gradually decreasing thing that slows down. So for example, in this case, we see that probably linear trend is not that applicable, right? Because so this doesn't look like a straight line. It probably looks closer to the parabola, right? So it increased faster in early 2000s, and then starting from 2010, the growth slows down. So probably the quadratic trend would be more appropriate here. So the second type of trend is a stochastic trend. The stochastic trend is random. That's why it is called stochastic. So it is trend, but it varies over time. So some periods it's kind of like fast growing, some periods it's flat, some periods it's decreasing. So the trend itself is random, which might kind of which might be weird, but still kind of this is the second type of trend, and we will talk about it later. So a stochastic trend might exhibit a prolonged period of increase, followed by a prolonged period of decrease, then again increase, then again decrease. So it kind of the trend itself is random, so it fluctuates, goes up, then changes the direction, or probably changes the speed of increase and so on. Yeah, an example might be is the inflation rate trend on the previous slide. So here was increasing, then decreasing, then flat. So might be that inflation has this stochastic trend. So we will start with deterministic trends. Basically, nothing is new here. In order to estimate the linear trend for Russian GDP per capita, you just need to estimate a usual linear regression model. You build a series of time periods, 1, 2, 3, 4, 5, 6, and so on. In our case, up to 25. And then you regress your time series on this variable t. So finally, you have the following estimated regression line. So real GDP per capita at the period t equals to 327.75 plus 1436. So what does this mean? This part. On average, every year, GDP per capita increases by 14,000 rubles. So per capita means per person, right? So per one citizen of a country. So on average, it increases with this rate. So both coefficients are significant, statistically significant. They significantly differ from zero. So that's why we can think of it as kind of average growth of GDP per capita. And this number also has a kind of usual interpretation. When t is 0, which means it's 1997, right? Because we started from 1998. This is t equals 1. So in 1997, real GDP per capita was this 327.75 on average again. Very simple. You know how to do this even from the past, even from the last year, from Econometrics 1. Now, if we fit the quadratic trend to the same series, quadratic trend yields the following equation. So with the negative coefficient on the squared term, which means that we have parabola with maximum somewhere. So we basically can identify this maximum. It is very simple. We just need to take the derivative of this variable, and we can identify at which moment of time GDP per capita would reach maximum. And when taking the derivative, we need to take this coefficient 34, 39 and divide this by 0.77 and divide this by 2. So 13, so basically around 13th moment, there is gonna be a reverse in the in the trend. But we have 25, which is also weird because some kind of the reverse in trend was somewhere around 2012, 2011. Well, might be. Make everything. Yes, well, basically that's correct. Okay. So now, what we can do with these trends? What is the practical use of trends? So first of all, the practical use is to again to model time series. You are not able to model time series with linear models discussed in the previous lectures because they are not stationary. So this series is not stationary. And in our case, if there is a linear trend model for GDP per capita, we can make a forecast for the next year, so for the current year, 2023, just taking the next value of t. So we have 25 observations in our data set. So the next observation would have the value of t equal to 26. So we plug 26 into the model, and we have the forecast of real GDP per capita of 701,000 rubles. So this is the forecast with the linear trend model. Then next year, when the new updated statistics would be published, you can take your forecast, our forecast, and compare with the real value of GDP per capita. If we are trying to make a forecast with the quadratic trend, we take this equation, plug everything again, t equals to 26 into this model, and our forecast is going to be almost 90,000 lower, 610.89 thousand rubles per person. Any questions related to the deterministic trends? Is anything difficult here? Is anything unfamiliar here? I believe, well, we discussed linear models, I mean OLS, a lot, and this is just one specific version of OLS. When instead of x you take t, the order of time period, and on the place of y you have time series values. Now, this is not all. If our goal is to model this series and build some kind of full model for real GDP per capita, simply building the trend is not a final step. So we have residuals. From every model we have residuals. Kind of starting from Econometrics 1, we spoke that every model has residuals. So residual is the estimate of the error term. In our case, residuals are the estimates of white noise, or so we hope that this is white noise. So what is residual? This is the actual observed value of real GDP in our case, minus the fitted value, right? So the value of real GDP that is estimated with the help of this, for example, deterministic trend model. So these are the deviations of a series from the deterministic trend. So in our case, look, we have actual series. This is the blue line. And the orange line is the fitted trend. So this is the quadratic trend. And you see that the blue line deviates from the orange line. Sometimes it's below orange line, sometimes it's above orange line, and so on. So it fluctuates around. So the residuals are the deviations of this blue line from the orange line. And we want to be as close as possible to this blue line in our modeling, in our forecasting. And of course, we want to predict in the future not only the trend part of our series, but also how far the actual series is going to be from the trend. So that's why we compute the residuals. And this is the plot of residuals. So basically, every point on the right-hand side plot is the deviation from trend on the left-hand side plot. So let's inspect it. For example, from 2001 to 2005, the deviations were negative. So the blue line was under the orange line. And here exactly we see that the residuals from 2000 to 2005 are in the negative area, right? So below zero. Then there is a sharp positive deviation from trend here in 2008, and this is exactly what we see here. So the deviation reaches almost 50,000 rubles here, exactly 550 or something like that, the actual value, and the trend is 500. And then again it goes down in 2009, then some period of positive values, then again below the trend, and so on. So again, this is the visualization of the residuals of the deviations of our series from trend. And we want to model this part right now. We want to separately work with this series, because these are also series. These are series of deviations. This is the autocorrelation function for residuals. This is partial autocorrelation function for the residuals. So ACF suggests MA1 model. EACF suggests AR1 model. Again, as usual, we are in trouble what to choose. But let's keep this question until later, because, well, in this case, we have a special type of series, and we will discuss this in a while. So, deterministic trend is something simple. You just fit your model, your series into the time periods, and that's it. So now, what about stochastic trends? So for the stochastic trends, there are also specific classes of models. And one of the most important examples of stochastic trends is random walk. So the simplest model of a variable with a stochastic trend is a random walk. So what is a random walk? A random walk is a time series of the following form: yt, so the current observation of the variable, equals to the previous observation of the variable plus the random component, plus the white noise. So epsilon is a white noise, so this is IID with zero mean and constant variance, as usual. So the basic idea of random walk is the following. So the value of the series tomorrow or today is just the value of today plus some unpredictable change. And the best guess of this series is just the series from the past. So the previous observation of this series. So the expected value of this series today is the observation yesterday, because you are not able to predict this part. Everything that you're able to gather about this series is the previous value, previous observation. This is not predictable. So the best forecast of tomorrow's value is the value today. The extended version of a random walk is called the random walk with drift. So drift means that there is some tendency to move upwards or downwards. So a random walk with drift can be represented with the following expression. So this is the usual random walk plus a constant beta 0. And again, so epsilon, so not u, epsilon is IID with 0 mean and constant variance. Expected value of a series today equals to this constant plus series yesterday. So basically beta 0 is the constant change in the series. So series always change by beta 0 plus some unpredictable part. If beta 0 is positive, yt increases on average by beta 0. If beta 0 is negative, yt decreases on average by beta 0. And the best forecast in this model is the value of the series today plus this constant drift beta 0. And we can compare this with the linear trend model, this random walk with drift. Basically, if we take yt in the linear model, linear trend model, and then yt minus 1 in the linear trend model, then look what happens. If I write down this part here, so there is yt equals to beta 1 plus yt minus 1. Basically, I plug this and this into the model of random walk and have exactly the same model. So linear trend model and random walk with drift are basically they are identical. But here we have constant, and here we have beta 1, which shows that our value increases every period by beta 1. So now, if our series follows a random walk, then it is not stationary. This is another type of non-stationarity. One type of non-stationarity is deterministic trend. Another type of stationarity of non-stationarity is a stochastic trend, and stochastic trend is a random walk model. Why this is not stationary? Because in the case of a random walk, the variance of this series increases over time, and the distribution changes over time. So it is easy to show. Let's start with y0 equals 0. Then y1 equals epsilon 1. So 0, previous observation, plus the random component today. y2 equals y1, previous component, plus error term this period, and so on. So yt is just the cumulative sum of these white noises, starting from 1 up to t. Now, what is the variance of this series at the period t? So variance of yt is the variance of this sum. So all epsilons are white noises. White noises are IID. Therefore, we can split this variance into the sum of variances. And this is simply t times sigma squared of epsilon. So the more terms you have in this sum, the larger is going to be the variance, which means that variance expands over time. The variance of yt explodes over time. And this is why variance of a series is not constant. Variance of a random walk is not constant. And therefore, this is non-stationary. Moreover, this variance increases without bound. So if t goes to infinity, variance goes to infinity. So the population autocorrelations are not defined. So it is not possible to define the autocorrelation of a random walk. And we can also link random walk model with AR1 model. So remember we spoke about AR1 model 2 lectures ago. This is a linear model when observation at the moment t depends on the observation at the moment in the moment t minus 1. If we set beta 0 equals 0 and beta 1 equal 1, then AR1 model becomes random walk model, right? Because this drops, and instead of beta 1 we have 1. There is going to be yt equals yt minus 1 plus epsilon, exactly the random walk model. If beta 0 is not 0 and beta 1 equals 1, then AR1 model becomes random walk with drift. And remember that 2 lectures ago we so basically I can open it. When we discussed linear models, we imposed this restriction. We imposed this restriction that phi 1 is not 1, right? So phi 1 is exactly the coefficient on yt minus 1. So this is what we have here. If this coefficient is 1, then we are in trouble because our model becomes a random walk model, either with drift or without drift. So we don't care, beta 0 can be 0 or beta 0 can be non-zero. It doesn't change anything. So what is the most important is that beta 1 is 1, and so stationarity condition fails here. So we formally showed that expected value of yt does not exist in AR1 model and here. So beta 1 in absolute value must be less than 1. In this case, yt is stationary. And in the general version, we also spoke about this somewhere, I guess here, when we spoke about general ARMA models. Yes, so yt is stationary when the roots of this equation are less than 1 in the absolute value. So this is just a different notation, but basically the idea is the same. So you take all the coefficients, and these coefficients are multiplied with by the values of some variable z. So you need to take the roots of this equation with respect to z, and if either root is one, at least one of the roots is greater than one, sorry, so smaller than one. If at least one of the roots is one or smaller than one, then ARP model is non-stationary. Yes. If ARP model has a root that equals 1, then the series is a unit autoregressive root or simply a unit root model. So this is the usual terminology. When we are talking about non-stationary time series with a stochastic trend, when we are talking about random walks, we call them a unit root series or series with unit root. So this is the usual terminology in time series econometrics. Yes, if yt has a unit root, then it contains a stochastic trend. And we call this series a unit root series. So if yt is stationary, then it does not contain a stochastic trend. Simple logic. Now, why we are so concerned with the stochastic trend? Why this is a problem? The problem here, well, basically, before this discussion, kind of, if you remember something from Econometrics 1, you may suggest, well, let's estimate this model and test whether beta 1 equals 1, right? And if it equals 1, then this is a unit root series. If beta 1 is not 1, then this is not a unit root series. Well, it might seem very simple for those who are familiar with the econometrics. But the problem comes from here. If this coefficient is 1, then something bad happens with the expected value of your series. It's not just that simple that, well, let's test this coefficient whether it is 1 or not. If it is 1, then everything fails. And this is the trouble. So if a regressor has a stochastic trend, then the OLS estimator of the coefficient and T statistics, they would have non-standard distributions. Again, because of this, because the series itself becomes weird. Expected value does not exist. So how is it possible that expected value does not exist? We don't know about this anything, right? So in econometrics, we haven't discussed anything about variables with infinite expected values. In statistics, we haven't done this. So basically this goes beyond of this course, what happens with the variable when expected value does not exist. But in our case, you simply need to understand that whenever you have a unit root stochastic, whenever you have series with a stochastic trend, whenever you have this unit root problem, hypothesis tests in a usual way are not applicable. T statistics are not applicable. So all the statistics have non-standard distributions. The estimator is going to be biased towards 0, even if the true value is 1. So you will never estimate 1 in the place of that coefficient. It would be always biased towards 0. It would always show you that, well, everything is fine, the coefficient is not 1. And yes, the t-statistic would have the non-normal distribution, and also if there are two series that are both having unit root, then they may kind of indicate some kind of mutual dependency between them, but in reality there is no, and this is known as a spurious regression. So in a nutshell, we cannot test that beta 1 is 1 using a conventional t-test. We need to come up with some special approach to this. Well, good news that smart people constructed this special test for us. And this test is called the Dickey-Fuller test. Well, in order to test if a series has a unit root, if a series AR1 model has beta 1 equals 1, we need to do the following. So basically, this is our model, AR1 model. Our null hypothesis that beta 1 is 1, and alternative hypothesis that beta 1 is less than 1. Why less than? So this is the left side hypothesis only, because of this. Because in absolute value, phi 1 must be less than 1. That is why beta 1 must be less than 1. Well, we do the following thing. We subtract yt minus 1 from both sides. On the left hand side, on the right hand side. And here we also factor yt minus 1 out, and we have beta 1 minus 1. So then we denote delta equals to beta 1 minus 1, and we, of course, this is the first difference, delta yt. And we have the following regression. And in this regression, we can reformulate null hypothesis and alternative hypothesis. So in this regression, null hypothesis is delta equals 0, right? Because initially we wanted to test beta 1 equals 1. So this difference must be 0 in this case, versus alternative hypothesis that delta is less than 0. This Dickey-Fuller statistic is computed using non-robust standard errors, homoscedasticity only standard errors. So we don't need to correct for the heteroscedasticity. And also there is an extension, which is called augmented Dickey-Fuller test, ADF test, which is an extension to the case of P lags in AR model. Basically, well, usually we call any kind of Dickey-Fuller test ADF. Doesn't matter. So in the ADF test, we do something similar. We take delta of yt and we regress delta of yt on deltas of yt minus 1, yt minus 2 up to yt minus p, and the past observation yt minus 1 times delta. So we also test the same hypothesis, delta equals 0, but there is this tail of deltas of yt minus 1 and so on. So again, the problem is that under the null hypothesis of a unit root, the ADF statistic does not have a normal distribution. You cannot compare ADF statistic with something like 196 in order to test the hypothesis at 5% significance level. So we need to use a special critical values for ADF test. And in our case, it is simply Python that spits out the value of a critical value of statistic and also p-value. With the help of p-value, it's even easier. So let's see how it works, both approaches. So the first approach, we estimate the following regression, delta yt on yt minus 1, and test whether delta here is 0. So we regress This is delta of our residual, and this is the lag of the residual. And look, the p-value on this coefficient is 8%. Well, basically, at the level of 5%, we are not able to reject the null hypothesis that this coefficient is 0, which means that we cannot reject the null hypothesis, and residuals may have a unit root. So this conclusion, in particularly, may explain why we have this result here, that ACF and PACF look so strange. So partially it can answer the question, why do we have that strange shape of ACF and PACF? So another way of doing this is to run augmented Dickey-Fuller test. Well, in Python, the code looks a bit ugly because, well, there is a function that runs such test, so it is called AD-Fuller, and you simply provide the series of residuals that, or like some other series that you want to test, showing also that you include drift here if there is a potential drift, and you indicate the number of lags in your model. So I indicated that there is one lag, but unfortunately this function does not have a kind of nice, good-looking output. So that's why we need to build it separately. So we take from ADF test, from this object, so 5 elements here, and 4 elements, sorry, and create a series which look like this. So this is kind of, this looks better. We also give them some names, and finally we have the test statistic here, -266, and p-value 0.02, which you can see is very close to the p-statistic from the previous test. But again, so this is just an illustration. So running Dickey-Fuller test in the form of regression is good for the illustration, but is not practical. So in practice, whenever you want to test if a series has a unit root, you need to apply this AD-Fuller function that provides you with the most correct and the most reliable result. So our conclusion is that the residuals derived from our deterministic quadratic trend model, these residuals have stochastic trend. These residuals have a unit root. And what is next? The unit root can be eliminated easily. If you have a series with a unit root, you are not able to apply either deterministic trend or AR model or MA model. This is forbidden. Your results are gonna be non-reliable. The first step you need to do, or you have to do, is to take the first differences of this series. So in our case, if there is a random walk model, first differences of YT would give you simply white noise, which is okay. We can test the hypothesis that the first differences of a series is the white noise. We know how to do that. For the random walk with drift, your first differences are going to be constant plus white noise. Well, again, it is easy to verify that this is true. So now we will build ACF and PACF for these deltas of residuals from the model of GDP. So this is ACF and this is PACF. And what do they suggest? Well, basically there are no autocorrelations and partial autocorrelations at any lag, which suggests that first differences of residuals are white noises. And if they are white noises, then residuals themselves are random walks without drift. And in total, we can write down the following model. So we have a deterministic trend model for real GDP per capita, but also there are some residual part that fluctuates over trend. And this part that fluctuates over trend follows a random walk here. So this, at every moment of time, you have a random component that that depends on the previous deviation from the trend plus the random part. And the overall model for the real GDP per capita in Russia is going to be this. Look, you have the deterministic quadratic trend part plus the deviation. So what is this epsilon hat t minus 1? This is the deviation of GDP from trend in the previous period. So this is how you would forecast the real GDP per capita, well, using our approach, let's say. So you need to update your forecast with the trend on the deviation from the trend coming from the past period. This is going to be the most reliable model based on our investigation, based on our analysis. So to conclude, the most reliable way to deal with the trend is to transform the series in the way that they do not have trend. And the residual part is can be modeled as the just linear time series model. In the case of deterministic trend, we simply fit our series into the linear or quadratic trend model, obtain residuals, and model the residuals with one of the appropriate linear models as I demonstrated here. In the case of a stochastic trend, the first difference of series does not have a trend, and then you can model these first differences. So for example, if there is a random walk with drift, you take the first difference, and then the first difference is going to be stationary. So it eliminates the random walk in series and gives you a chance to model time series in a conventional way. Also, another important thing is that even if you fail to reject the null hypothesis of a unit root, it doesn't mean that the unit root is actually there. So sometimes, of course, every hypothesis test can give you some misleading results. So for example, if there is AR1 model and the true coefficient is 0.98, so ADF test would probably signal that there is a unit root. But in reality, you will have AR1 model with a high level of persistence. But still, it's going to be stationary. So that's why, well, it kind of makes our life more difficult because we need to somehow collect some additional uh, evidence in the favor of stationary or non-stationary model. But this is beyond of the course and beyond of the scope of this lecture. So this is all that I wanted to tell you about trends, about the first type of non-stationarity. Questions? Yegor, Khan. Well, then let's take a 20 minutes break. Now it is 14:50 in Irkutsk, so let's continue in 15:10 with the last lecture. See you later, guys.